Some exponential equations can be solved without having to use logarithms, but instead by finding a common base between the two sides of the equation, because if we have a common base, then that means the exponents must be equal to each other. Now that's not always possible, but in the two examples that we have here, it is. So for the first one, our two bases are 4 and 8. If we can somehow make those two bases the same, then we would be able to just set the exponents equal to each other. So 8 is not a power of 4, but those are both powers of 2. So what I'm going to do is I'm going to replace 4 with 2 squared, and then that is going to be still raised to the 3x power. And then on the other side, 8 is 2 cubed. So I'm going to replace 8 with that, 2 cubed, and then that is still being raised to the x plus 1 power. Now, when I raise a power to a power, we multiply those exponents. So I'm going to do that on both sides. So I'm going to end up with 2 to the 6x over here on the left, and then I have a little distributive property here, so I'm going to end up with 2 to the negative 3x plus 3 on the right-hand side. And so now, as long as my bases are the same, then that means my exponents have to be the same. Otherwise, these two sides would not be equal to each other. So I'm going to just get rid of the 2's, and I'm going to say 6x has to equal negative 3x plus 3. So we now just bring the 3x over to the left. We end up with 9x equals 3. So if we divide both sides by 9, we get our solution, x equals 1/3. For our second example, we've got 1/27th as the base on the left. We have 9 as the base on the right. So again, 27, it's in the denominator, so that creates an issue for us. And 27 is not a power of 9, although hopefully we recognize that these are both powers of 3. So similar to what we did on the previous question, I'm going to try to rewrite both of these bases in terms of the same base, just this time it's 3 instead of 2. So 27, we can think of that as being 1 over 3 to the third. 27 is 3 to the third. Then I still have that being raised to the negative 2x. And then on the other side, I've got 9. I'm going to rewrite as 3 squared, and then that's being raised to the 2x minus 1. Now the additional complication is that 3 to the third is in the bottom. I need that 3 to the third to be in the numerator, so I'm going to move it up by making that exponent negative. So I've got 3 to the negative first to the negative 2x, or sorry, 3 to the negative third to the negative 2x is equal to, and then on this side I'll still leave it as 3 squared to the 2x minus 1. So now at this point we're ready to go ahead and multiply these exponents together on both sides, raising a power to a power. So over here on the left we're going to end up with 3 to the 6x, and then on the right we're going to end up with 3, again, little distributive property, to the 4x minus 2. And so now that I've got the two bases the same, I can set the exponents equal to each other. So I end up with 6x equals 4x minus 2. And so then if we subtract 4x from both sides, we end up with 2x equals negative 2. So finish off by dividing both sides by 2, and we get x equals negative 1. Now we're not always able to make it so that both sides of the equation will have the same base. So for example, 6 to the x equals 24. It's tempting to think that there's some way to make 24 into a power of 6 because it's divisible by 6, but indeed we can't do it. So the only way we're going to be able to solve this, the only way we're going to be able to get the x out of the exponent so that we can figure out what x is to solve using logarithms. And so one way that we can approach this is to just rewrite this in log form using our pattern. So the base of my exponential is 6, so the base of my logarithm is going to be 6. Then what is the output of my exponential is going to become the input into my logarithm. So log base 6 of 24 is going to equal my exponent, which is x, since a logarithm is an exponent. Now to get a numerical value for x, besides leaving it in log form here, we're going to have to either use an inspire, where we can use any base we want, but if we're working with a regular scientific calculator or the other graphing calculator type, then we're going to have to use our change of base. So if you'll recall, we can rewrite it in terms of log base 10 or log base e so that it is calculator friendly. So I'm going to go ahead and use our common logs, log base 10. And so the change of base pattern says whatever's the input here is going to go to the numerator. So that's going to be log of 24 over log of the base, so log of 6 equals x. So now I can turn to my calculator. Log of 24 is 1.380 if we round off to the nearest thousandth. And then I can push buttons on my calculator to get log of 6, which is 0.778. And then if I divide those two results, we get x equals 1.774, which, if we go back to the original question, looks like a pretty reasonable answer. 6 to the first would equal 6. 6 to the second would equal 36. So that means x has to be somewhere between 1 and 2 for us to get an answer of 24 when we raise 6 to an exponent. So 1.774 satisfies that. In our second example, before we can rewrite it in log form, we're going to need to isolate the exponential. So the first thing I'm going to do is add 14 to both sides. So I get 3e to the x equals 25. And then I still need to divide by 3 to completely isolate my exponential. So I get e to the x equals, I'll just leave it as 25 thirds. So now at this point we're ready to rewrite this in log form. So the base of our exponential becomes the base of our log, so that's log base e, which of course we're going to write as ln instead of log base e. The output of my exponential becomes the input into my logarithm, so that's 25 thirds. And then that equals the exponent, which in this case is x. And so now I'm just ready to push buttons on my calculator. And just be careful, it's not natural log of 25 divided by the natural log of 3, it's the natural log of 25 thirds. So that's what we're going to enter into our calculator. And so we get x equals, when we're all done with that, 2.120 if we round off to the nearest thousandth. The last example is the trickiest because we don't have just one exponential, we have two. And so for us to try to just rewrite this in log form, it's going to be a little bit tough. Which base do we use? It's going to become pretty complicated. So instead, just like we can add something to both sides of an equation, just like we can square root both sides of an equation or square both sides of an equation, we can take the log of both sides of an equation. And I'm going to take the log of both sides using one of the two exponential bases as the base of my logarithm. And we'll see why in just a moment. I'm also going to choose to use the base of my logarithm as being for the part of the equation that has the more complicated exponent. So the x plus 1 I would say is slightly more complicated because it's got two separate terms as opposed to the 7 to the 3x which just has one term in the exponent. So for that reason, I'm going to take the log base 5 of both sides. So I've got log base 5 of 7 to the 3x equals log base 5 of 5 to the x plus 1. So I do have to take the same log base of both sides. I can't do base 7 on one side and base 5 of the other. And I could have done the log base 7 of both sides and I'd still work out to the same answer, but I think we'll see in just a moment that it works out a little bit easier for us if we choose the side that has the more complicated exponent and use that base. So how do we solve from here? Well, the whole goal of using logs here is to get the x out of the exponent so that we can eventually solve for it. And so the way that we're going to be able to do that here is I can take this 3x using my log of powers and bring it to the front. And I can take this x plus 1 as the exponent on the inside of my logarithm and bring it to the front. So that means I'm now going to have 3x times the log base 5 of 7. And on the other side, I'm going to have x plus 1, I'm going to bring that whole exponent to the front, times the log base 5 of 5. And over on this right-hand side, hopefully we can see the payoff of taking the log base 5 of both sides, because here I have the same base as I have inside the input of my logarithm, which therefore means I'm going to get a result of 1. So this side here is just going to be x plus 1. X plus 1 times 1, so just x plus 1. over on the left-hand side, I've got 3x times this log base 5 of 7, so I'm going to need to use my change of base in order to figure out what that number is, because I can calculate what the log base 5 of 7 is. I just need a calculator to do it. So I'm going to do exactly that. I'm going to rewrite this as log of 7 over the log of 5. So I'm just rewriting it in a calculator-friendly base. I could have used natural logs here as well, but I chose to use the common log. So now I'm going to push buttons on my calculator to figure out what these two values are. I still have this 3x here. And so if I push buttons, the log of 7 is 0.845, and the log of 5 is 0.699. And so that is still equal over here on the other side to this x plus 1. And so now over here on this left-hand side, I just have a bunch of multiplying and dividing that I have to do. It's 3 times x times 0.845 divided by 0.699. So I'm just going to do that all in my calculator. And so ultimately, we end up with 3.627 times x. So 3 times 0.845 divided by 0.699 is 3.627. Then again, on the other side, I still have this x plus 1. And so then my last thing I need to do is solve for x. I've got gruesome numbers in the problem, but I can do it. So I'm going to just subtract x from both sides. So we get 2.627 times x equals 1. And so then my last step is to just divide by 2.627 on both sides. And so now, again, one more round of pushing buttons on our calculator. And so we end up with our result of 0.38. Make that look like an 8-1. And if we go back to the original problem and plug that in, we can estimate in our head that that seems about right. If I multiply 3 times 0.381, that's a little bit more than 1. So on this side here, 7 to a little bit more than 1 is going to be a little bit more than 7. For the other side of the equation, if I plug in 0.381 plus 1, it's a little bit bigger exponent, 1.381. And so when I raise 5 to a slightly bigger exponent, it makes sense that that'll equal a little bit more than 7, like we're getting on the other side. And we can plug this in on our calculator and verify that this indeed is correct, but a little mental math will get us there.